Cambridge AS Computer Science, Chapter 3, Hardware, Embedded Systems. Let us start studying embedded systems. Embedded systems is a computer control system. An embedded system is a computer-controlled system with a small computer inside of it that cannot be used for anything else. This is in contrast to the computer system that is multi-purpose, where you can put some programs and change programs as much as you wish. So an embedded system is a dedicated system with a computer living inside a device. Okay, so an embedded system is a microprocessor-based computer hardware system with software that are designed to perform a dedicated function. So, for example, you may have an air conditioner and a computer inside that air conditioner, and we call this embedded system because that computer is forever inside that air conditioner, and it is almost impossible to use it for anything else. Okay, so this is an embedded system. Okay, so the system will do a function. Okay, at the core of is an integrated circuit designed to carry out computation for real-time operations. Okay, an embedded system is a microprocessor or a microcontroller within a large system that perform one specific task. Okay, so it is dedicated. Embedded system in washing machine can only controls the program for the washing cycle. It is part of the washing machine but does not perform any other function within it. So this is an embedded system. Let us go through as many examples as we could. Okay, so one of the examples of an embedded system is modern television. Many modern televisions are examples of embedded systems. These televisions are embedded systems because the embedded system is integrated into the TV. So maybe the question was asking why this is an embedded system. Because the embedded system is integrated into the TV. The computer is inside of the TV and can never be taken out of that TV to do something else. Okay, so that's an embedded system. An embedded system is a combination of hardware and software. Any system or any computer system is a combination of hardware and software designed for a specific function. So it is embedded, so it is for only one specific function. The system is not easily changed by the TV owner. You cannot easily change that computer to control anything else. It is forever inside that television, so it is an embedded system. The program for the embedded system may be on a ROM or EEPROM. What is that? E stands for EEPROM, stands for electrically erasable, programmable, read-only memory. So originally it was a read-only memory. It was a read-only memory that came with the embedded system with a permanent program where it is impossible to upgrade. If it is just ROM, it's impossible to upgrade. But being electrically erasable, and it is a programmable ROM, now it functions as if it's a memory card or an SSD drive. Then it is much easier now to be updated, to be upgraded, without the need of taking that device out of the system, without technicians. Okay, so embedded systems use electrically erasable, programmable, read-only memory ROM. So no additional equipment is needed to change data. Sometimes you need to change data, for example, upgrade or modify the system. Because it is electrically erasable, the modification can be done very easy. This enables firmware. What is firmware? Permanent programs. This enables firmware updates by non-technical users. You don't have to be a technician to upgrade the system. Automatically upgrades because it is just like it has a flash memory drive. Okay? EEPROM, electrically erasable programmable ROM, can be erased and replaced and reprogrammed several times. Okay? So the firmware can be updated or can be erased or can erase a particular byte or the whole EEPROM. So using EEPROM, it is like it is using an SSD. It is very easy to be upgraded. It is very easy to be erased. It is possible to reprogram and update without removing the device. I think we studied EEPROM, electrically erasable programmable ROM, at the beginning of this chapter when we were studying the ROM, because electrically erasable programmable ROM is a modification from a ROM. Okay, so that was a bit talking about the embedded system using an EEPROM. Okay, sometimes we call it E² PROM. Okay, let us take another example about an embedded system as a car alarm system. Okay, sensors could be used in the car alarm. Sensor would be sound sensor. Okay, يبقى one of the sensors that can be used in the car alarm system is a sound sensor. If a sound occurs inside the car, the alarm is activated. You have the car closed and locked and supposed to be nobody inside of it. And if you can hear some noise, if the sensor can pick up some noise from inside of the car, this is interpreted as an intruder. So if a sound occurs inside the car, the alarm is activated. An infrared sensor senses the heat of the person in the car. So we would like to protect the car with as many sensors as possible. A pressure sensor can senses an intruder sits on the driver's seat. So if somebody sits in the driver's seat, the pressure sensor detects that intruder. The car alarm is an example of embedded system. The characteristics of an embedded system is that the embedded system is built into the car alarm. So it is permanently built into the car alarm, cannot be used for anything else. That's why we call it embedded. An embedded system is a combination of hardware and software designed for a specific function. It must have a processor. It must have a memory. It is like a computer, but a small computer. Input and output. Inputs are normally from sensors. Outputs are normally to actuators to control things. The system is not easily changed or updated by the car owner because it is an embedded system. Okay, the last thing to say about cars, as you can see, there are so many embedded systems in cars. Car alarm, okay? Okay. A car has several features. One feature is lane detection system. The computer inside of the car can see, using a sensor in the front of the car, it can see the lanes. Okay, so one feature is a lane detection system. The system monitors the lines on either sides of the lane. If the car gets too close to one line, the system automatically moves the car away from the line. So it is an embedded system. The lane detection system is an example of an embedded system. The lane detection system is built into the car. The lane detection system only performs one task. That's why we call it embedded system. The lane detection system is not easily upgraded, changed by the car owner. Other features. What are other possible features in a car? Record the number of miles traveled in the current journey, from where the engine is turned on to when it is turned off. This is another example of an embedded system in a car. Record the total number of miles the car has traveled since it was built. This is another example of an embedded system in a car. Okay, let us talk about monitoring and control systems. Let us talk about, so an embedded system could be a monitoring system, or an embedded system could be a control system. Okay, so let us see all these monitoring and control systems. Okay, let us study this diagram. Let us study this diagram to know exactly the differences between a monitoring system and a control system. There are things in common. What is a monitoring system? Measures quantities, and if they are out of range, the system only gives an alarm. This is called a monitoring system. For example, monitoring the temperature of the atmosphere, or monitoring pollution levels in a river. This is just a monitoring system. However, a more complex system or a more functioning system would be computer control or control system, where, for example, if the temperature is too cold, the computer can take action. And that action would, for example, be turn a heater on. Or if the temperature is too hot, the computer can take an action. For example, open windows or turn on a fan, for example. Okay, so let us study this diagram. A sensor is a hardware device that measures a property and transmits a value to a controlling computer. You may have a temperature sensor that senses the temperature. You may have pH sensor that measures the acidity or alkalinity of a liquid. This could be in a chemical factory or could be in a river where you suspect to have pollution. Okay, so a sensor is a hardware device that measures a property and transmits a value to a controlling computer. On the other side, an actuator is a device that receives signal from a computer and adjusts the setting of a controlling device. For example, an actuator would turn a heater on. An actuator would turn a heater off or change its temperature. An actuator would switch a fan on or switches a fan off and control its speed. So a sensor in a control system, a sensor is the input device, the actuator is the output device. Okay? Okay, let us look at this diagram. In both computer monitor and computer control, we have to go till here and then we stop and do classified. Okay, in both computer monitor or computer control, we have sensors that send signal to the microprocessor. So typically input is through a sensor. We have sensors that send signal to the microprocessor or microcomputer. Signals are converted from analog to digital if necessary. Okay, using an analog to digital converter. For example, a temperature sensor would needs an analog to digital converter. Even a sound sensor would needs an analog to digital converter. Why? Because sensors produce analog signals and the computer can only understand and deal with digital data, ones and zeros. Then the computer analyzes the reading and compares with preset values. And then here the two systems differ. If the computer is monitoring, if the data is outside the acceptable range, the computer only produces a warning. So if it is only computer monitoring and the reading, it is too hot or too cold, the computer would sound an alarm. And that's it. Why? Because it is just a monitoring system. However, if it is a control system, if the temperature is too cold, the computer will switch on a heater. If the temperature is too hot, the computer will switch on a fan or open a window for ventilation. So, and this is called feedback. So feedback in a control system, there is some sort of feedback because the system changes the temperature and the temperature is input again to the system. So it is kind of closed loop. Okay? So that was a bit about monitoring and control system. Differences between monitoring and control system. Monitoring only gathers information, but control systems also perform actions. Output in a control system can affect the input. There is no feedback. Feedback is only available in control systems. There is no feedback in a monitoring system, while a control system relies on feedback. Okay? So this is monitoring and control system. Examples of computer monitoring and also examples of computer control. Okay? And let us study few examples and then we go to the classify and solve. Examples of computer monitoring. Monitoring a patient in a hospital where vital signs are monitored, like for example, breathing rate, blood pressure, heart rate, temperature. Okay, this is just a monitoring system because if the conditions worsen, the system would only send an alarm to the nurse, and that's it. So it is a monitoring system. Monitor of intruders in a burglar alarm system would send an alarm to the owner. Monitoring a temperature level in a car engine. If it gets so hot, you get this displayed on the dashboard, and that's it. Monitoring pollution levels in a river. You measure the pH of a river. If it is not 7 and it is not neutral, it is not clear, then it is polluted. Okay, so these were examples of computer monitoring. Examples of computer control. Turning street lights on at night and turning them off again during the daylight. So the computer automatically controls the lights, regulating the temperature in a central heating or air conditioning. When the temperature is so hot, the computer can turn on the cooling unit or increases the speed of the fan. Regulating the environment in a greenhouse, where you have plants and monitor temperature and light and humidity. Changing the traffic lights at the road junction, operating anti-lock brakes on a car when necessary. Okay, so let us answer these questions. Car speed display, this is just monitoring. Aeroplane autopilot, this is control. Roller coaster, where it's a game in an amusement park and the computer is controlling that roller coaster. Recording the rainfall at a weather station, this is monitoring. Robots loading a part onto a conveyor, this is control. Okay, let us go through few other examples and then we do the classify. Let us go through these few examples. Monitoring earthquake activity. Sensors send signal to a computer. Everything will follow this model. Sensors send signal to the computer. Signals are converted from analog to digital. Signals are compared to preset values. So, monitoring earthquake activity. Sensors send signal to a computer. The signal is converted to digital using an ADC, analog to digital converter. The computer calculates the activity of the earthquake based on sensor signal. If the calculated is above a certain value, then it is a severe or dangerous earthquake. Then the location of the sensor is determined, which one is giving an alarm, and use a map of activity. The location and magnitude are sent to a printer via USB or link. Monitoring is continuous, which means every few seconds it monitors another read. Okay, warning from earthquake monitoring, a speaker or a buzzer to give an audible alarm rather than flashing lights or red flashing lights, rather than print them out. So that was an example of monitoring earthquake activity. Then another example of controlling. So this is controlling. Controlling temperature in a swimming pool. It is very simple. Measure temperature, change temperature from analog to digital, compare temperature with preset value, and then do two ifs. If temperature is below set value, turn the heater on because it is getting very cold. Okay, and wait another period of time. If temperature is above a set value, turn the heater off because the heater is heating the water too much. And the process repeats. And here in this example, the temperature is around 28 degrees. So an indoor swimming pool is to be kept at a constant temperature of 28 degrees. Sensors continually measure the temperature of the water in the pool. The stream of reading is sent to a processor and compared with 28. If the reading is out of range by a set amount, then the actuator turn the heater on and off as necessary. So, for example, if temperature is below 28 by 1 degree, the computer turns the heater on. If it is above 28 by 1 degree, the computer turns the heater off. Okay, and that range to avoid repeatedly turning the heater on and off, and then it will be damaged. Feedback ensures that the water temperature remains close to 28 degrees. So this is feedback and keeps the temperature around the 28. So this is a diagram about feedback. What is feedback? When the output affects the input. When the input is a temperature sensor and the output is using a heater that affects the temperature. So it's kind of loop. So you input to that loop the desired value for output. What is the temperature you like to? Into the controller. And also the computer using sensor knows the actual temperature. And then compares. If it is lower, send to the actuator to turn the heater on. If it is higher, for example, temperature, send signal to the actuator to turn the heater off. Turning the heater on and off affects the temperature. And the input is through a temperature sensor. So it's a loop like this. Okay? This is called feedback. Importance of using feedback in a control system. Feedback is used to ensure that a system operates within the given criteria by enabling the system output to affect subsequent system inputs, thus enabling the system to automatically adjust conditions. So if it gets too hot, the system will turn the heater off. If it gets too cold, the system will turn the heater on. And then it repeats. So you have a closed loop like this. Microprocessor or computer. We say microprocessor when it is a very small computer. It is not a real computer. It is just a microprocessor or a controller. Okay? Digital measured value from an analog to this is the control the environment. You have here a sensor and here an actuator. The sensor, for example, measures the temperature. The actuator, for example, turns a cooling system or a heater on or off. Okay, so the sensor measures the temperature, an analog to digital converter changes it into analog and into digital. The digital measurement is input to the computer takes decision and then decides to turn the heater on or off, and this could be done through a digital to analog converter. What other examples do we have? Maybe 2 or 3 other examples. The washing machine. The washing machine is an example of an embedded system, and it is computer controlled. The refrigerator is an example of an embedded system, and it is computer controlled. And the cake factory is very recently copied from the past paper. Okay, that question was very recent in the past paper. The washing machine's embedded system make use of both random access memory RAM and read-only memory ROM. The RAM stores the choices for the washing program. So your current choice, the user has entered, store the data from the sensors, and store the time left in the program. The ROM stores the startup instructions for the washing machine. So it looks like you need here RAM and ROM. Okay. Refrigerator. Temperature in the refrigerator must be kept below 4 and 6 degrees Celsius. Must kept between 4 and 6 degrees Celsius. The microprocessor in the refrigerator turns on the cooling if the temperature is too high and turns off the cooling if the temperature is too low. The system in the refrigerator is a control, not a monitor, as the system uses feedback. And the system produces an action that causes the temperature to change. So if the system causes an action, then it is computer control. If just only give warning, then it is computer monitor. Let us study that last example and go to past papers and so on. A cake factory uses machine to make cakes. The factory uses a monitoring system to record data such as the number of cakes being processed each hour. Okay? When data collected from the sensor and analyzed and used as feedback, it is a control system. So when it uses feedback, for example, when that tin is in position, it starts pouring the cake or the fluid or so. When the weight reaches a set level, stop pouring. Okay? So it uses feedback. It is a control system. One example of this system was the factory to maintain a constant temperature in the oven by turning the heater on or off. It uses a temperature sensor to measure the value. Cake mixture is mixed in a larger pot, a conveyor belt, as you can see. Move the cake tins underneath the pot. The conveyor belt stops at a set quantity of cake mixture fills the tin. So there is a sensor to detect the position of the tin. And then the nozzle starts pouring. And there is a pressure sensor underneath until a certain weight or a certain amount of cake is poured, the nozzle stops. Okay, and then starts moving again for the next tin. The infrared detect the tin in its correct position. We use an infrared sensor. Okay, when the infrared sensor detects the tin in its correct position, a signal is sent to the microprocessor, which sends a signal to an actuator to stop the conveyor belt and send a signal to another actuator to release the cake. So once the infrared sensor senses that the tin is in position, the microprocessor sends a signal to stop the conveyor and then another signal to start pouring the cake mixture. Then we have a pressure sensor to measure how heavy the weight of that mixture. A pressure sensor continuously record the weight of the cake mixture in the tin. and send the reading to the microprocessor. The microprocessor compare the reading with a preset value. So for example, 1 kilogram. If it is just a little bit above 1 kilogram, the nozzle stops. When the weight of the cake mixture in the tin matches the desired weight, the microprocessor sends a signal to the actuator to stop releasing the mixture and send a signal to another actuator to move the conveyor belt. I have to stop here because I cannot start logic gates until I completely solve plenty of questions.